So reservoir engineering insight number one, robbing PDP to pay PUD. PDP, of course, is proved developed producing reserves as opposed to proven undeveloped reserves. So I'm going to, rather than sort of talk theoretically about this, I'm going to show you guys a real live example. And this comes from a presentation that was presented by Continental Resources a few years back. And they use decline curve analysis, as most companies do, to do their reserves. And as you can see, we have a decline curve shown here. This is a 40-year production forecast, constant B-value of 2.07, and the EUR comes out to be 425,000 barrels. My first question, as yours should be as a petroleum engineer, is this a realistic production forecast? Okay, we can't always answer that question just by looking at it, but we're going to dig a little bit deeper and try and find out. So this particular development is in the Williston Basin, and I'll get into the geology a little bit more in a minute. The Mathestad 2-35 well. The original wells that were drilled, so there's two layers of interest here. One is the Middle Bakken, and one is the Three Forks, and the Three Forks underlying the Middle Bakken. So there were two initial wells drilled there, completed, as you can see, the first one there completed in June 2009. And so there, in terms of lateral spacing, we've got a full section, and one well is kind of over top of the other one. And so they, in essence, they have unbounded lateral drainage when they're first drilled, of course. But the question that's going to come up later on is how do we develop this field going forward? So let's take a look at the data again. There's our production data. There's our decline curve analysis. Again, 40-year EUR. So let's talk a little bit about decline curves. Again, if you're a petroleum engineer working in reserves, this stuff is very basic. We use the B-value to relate to how we believe that forecast is going to progress, right? And a lot of times it's related to the drive mechanism in the reservoir. The two red bullets at the bottom have become much more important as our industry has progressed into unconventionals and tight reservoirs, because that drives the B-value up. So long-term linear flow should have that B-value of 2. So that's probably a reasonable forecast using a B-value of 2. We would expect this is a low permeability reservoir. We would have a long transient forecast involved. So as a reservoir engineer, I use rate transient analysis to do production forecasting, and I always like to compare that to decline curve analysis. Many of you have heard me talk probably a lot about this in the past. We use a model, and we try and generate a forecast based on the model. So what I wanted to do is see, is this a realistic forecast? And based on 13-20-foot spacing, that's, we get an EUR of 412, 425. All right, so it's based on those volumetrics, that's a realistic forecast. So I'm okay with that. So the model in this case supports the decline curve analysis. Now that's assuming 320 acres, so that would assume that we're going to go and drill 2 wells per section. So this is their field development plan. Their field development plan at the time, I don't think they're drilling any of these wells now, but at the time was quite aggressive. They're going to go down to 660-foot well spacing. So that brings the volumetrics down to a much smaller tank size. So this is one of the areas where rate transient analysis and reservoir modeling can add some value, because I can build a model with a larger drainage volume, which I've already done, and then I can build a what-if model for smaller drainage volume. So in essence, I'm going to test their idea of downspacing and see if that's still consistent with the type well or the type curve that they're using. So let's do that. So there's our decline curve analysis. There's our match with the volumetrics of half-section spacing, which we showed already supports the existing forecast. But this is what happens when you move into 660-foot well spacing. What we see is a dramatic drop in future production. Now, of course, you don't see this at the beginning. At the beginning, they're fairly closely aligned. It's only later on when the boundaries are reached where we start to see that very pronounced departure from that original forecast. And it's to the tune of almost 50% reduction in 40-year EUR. So what does this all mean? Well, we can look at the same thing on CUME, and we can see there's a remarkable difference between those two forecasts. So, let's kind of bring this all back to the original concept, robbing PDP to pay PUD. The problem with the approach of just using a static decline curve as a way to forecast new wells that are drilled is that it doesn't take this volumetric dependency into account. So production decline changes when infill wells are drilled. If you're a petroleum engineer and you do this sort of stuff, it's like, duh, we all understand that, of course. When I talk to the investment guys, their jaws sometimes drop when you show them this, because a lot of companies will routinely do this sort of thing. They'll use the type curves. They won't take into account the impact of downspacing. So DCA-based type curves are usually not adjusted to account for the impact of infill drilling programs. So the last point, I think, is the most critical. The optimum drilling density in a field development scenario often requires this. So it's not a bad thing to rob proved reserves to pay your PUD reserves, because it will allow you to accelerate production. Okay? Economically, it often makes sense to do that, but you have to account for it. Right? It's more of an accounting issue than anything else. You're going to overstate your reserves if you don't do it. So the plot that I'm showing on the bottom, I generated for this Three Forks Bakken play, and what you're looking at here is modeling. The blue curve models all sorts of different well spacing scenarios, all the way up to 8 wells per drilling spacing unit. And of course, as you can see, our EUR per well starts to drop immediately after about 2 wells per section, which is what our forecast showed. So the place where you're starting to rob producing reserves to drill new wells happens after only 2 wells are drilled in that section. The other curve shows the net present value. So that's the economic picture for the exact same model. Okay, so that layers in some economics. And what that shows us is that the optimum drilling density to maximize NPV happens at 6 wells per DSU. So that gap between those two things is telling you that, in order to make this now this is for the economics of the time. I don't know if this would be the case anymore. But in order to make this, to get to drill to this density, you're going to have to do some proper accounting on the reserves and not just use static type curves. Otherwise, you're going to overstate your reserves.